Hello, welcome to the stream. We're back with more Essentials of Compilation in Gleam. We are working through Chapter 6. If you have just joined me for the first time, Essentials of Compilation is a textbook about how to build a compiler from tip to tail. And it is a really remarkable book in that it is a way of learning compilers, compiler construction that focuses on small steps in the compilation process, but also small enhancements of the source language. So you're not expected to start from a fully realized, fully functional Turing complete language and build all the parts. It's like the draw the rest of the owl sort of thing. In this, we start with a very simple language and we gradually add features to it for the high level language. And we've been working on this, I think it's since February of this year, in little 2 to 3 hour chunks. And it's been really interesting for me personally because compilers was my favorite class in my CS degree over 20 years ago. That tells you how old I am. But we really only did the front end. We did lexical analysis, syntactic analysis, also known as parsing, and some semantic analysis, which, like in that situation, was not really type checking. It was more like gosh, I can't even remember. It's been too long, but we didn't get very deep. This approach in Essentials of Compilation goes from our very first thing, our very first completed unit should emit x86 assembly, which is like, oh wow, so you start from the very high level and you immediately go down to what is the closest thing that we have to machine code, and then we build on top of that. So that's I think that's awesome, and I really love the approach, and I really love the figuring out how to tweak things as we add new features. Anyway, so that's the overview. The original book is in Racket. Racket being a very popular Lisp. And we are doing it in Gleam, which is a new-ish, I guess, 1.0. Gleam 1.0 was only a year ago. So Gleam is very young language, strongly typed, and it runs on the Erlang virtual machine known as the Beam, as well as it compiles to JavaScript. So you can run it in Node.js or in your browser or any other place that runs JavaScript. Okay, so where are we at? Last time we were looking at what is known as tuples or tuples. In Racket, they're called vectors. And essentially they are fixed length heterogeneous collections. So tuples are like the basis of structs in many languages, essentially, in that you can have you have a fixed number of fields, and the names of the fields, basically, when you compile them out, get turned into either indices into the vector, or they get it turned into like offsets from the base of the pointer to that structure. So we have the ability to create heterogeneous collections, but because we're not building a language that has explicit memory control. What we did last time is we injected into one of our intermediate languages the ability to call a garbage collector. So call the garbage collector if we are out of memory on the heap, and then also like allocate memory on the heap. So those are the things that we did last time. It was in a phase called expose allocation. So let's switch over to the editor. Here's where we were last time. This is a sample program that is in the book, and we always have the book up here. So this is what their example compiles into. I say compiles, when it passes through this expose allocation phase, which we were talking about in the last time, this is what gets emitted. And you note here that we have some calls to the garbage collector. It's like, you know, if we add 16 bytes to the free pointer, is it at the end of the free space in the heap? And if it is, then try to collect 16 bytes. And if it's not, you know, if there's plenty of space, then you just skip it, and then you allocate a vector of size 1. And this takes 16 bytes because the vector has a tag on it, a one word, so 8 bytes tag, as well as the tag for, or the slot for this integer that's contained in this vector. And then after we've allocated, we call the vector set, which just sets the field. So set the field 0 to 42. You can see that here. It's just saying we're constructing a vector, and it has 42 in it. The way that that gets compiled out is you allocate the vector, and then you fill in the slots. This is called, in lots of languages, memory initialization. So that's what this is doing. And then you go and you take care of the outer vector, which contains a vector of integers, right? So again, it needs 16 bytes. It needs a tag, just like this other one did, as well as a pointer to the other vector. Okay, and then so you can see here that actually this alloc2 here, which gets assigned via this let binding to vec_init6, it's really a pointer. It's just not, it's not exposed at this level. We're once we get underneath the high level language, we have fewer guardrails. We have fewer things that are actually going to be checked, and we have to make sure that, well, our code is correct, because we're not going to go like generate this phase and then go type check it. You could. That would be really weird though. So yeah, once you get past the front end, your guardrails can kind of be taken away, and you have to be very conscientious. Anyway, so those are pointers, and then there's this outer vector ref, which is just get me the value of this field. And it's like, so we constructed a vector which contains a vector which contains 42. Give me field 0 out of it. So now you're going to get this inner one, and then give me field 0 out of that. So you're going to get the 42. So like so many examples in this book, they're obsessed with 42. So the result of this program should be 42. Okay. So we were writing this test, and I think that we did a rough check, and where did I throw that? I think I had a, no, I might have done it inside a example, and we just like looked at the AST, because we do not have pretty printing of our intermediate forms. It's something I'd like to do on a side quest soon, is just get every single one of our intermediate languages having pretty printing, and then they can emit examples that look like this, and we can do sort of comparisons. Okay. Well, let's... Another thing that might be interesting is to have like a version with holes. And what I mean by that is the naming of these variables is completely incidental, right? So we did this, you know, following along with their example. We said we're going to use vec_init for these blocks where we're initializing a vector, and we're going to use alloc for where we're for return values of calling allocate, and that's all well and good. And then like for the throwaway bindings, These lets are in there to make sure that we sequence correctly. They're not there for any other purpose than their side effect. But we just like have an underscore, and they have _4 and _3 and so forth, _8. We tried to get our program to line up correctly with this example, but it didn't quite. So like if I run Gleam test here, and note that our test, it just echoes the result of this, so it's going to be really flat. So we can, like, you know, this is a copy. Okay, so this is what the output of that looks like. Interestingly, we have a different, and I think that we ran into this in one of the other chapters. This is flattened in a way that we do not do. I say it's flattened in that, look at this let. That is not in this. But let's get this. Let's read through this. So we have vector ref and vector ref. We expect that. And then we have a let, and this is vec init 5. So this comes out differently. And then we have a vec init 1. Now this 42, so we're binding 42 to vec init 1, which is interesting. And I think that we talked about this last time, that we aren't looking at what the initial values are in that vector, whether they're immediates or not, because we don't have that sort of like, is this thing atomic at this phase? Expose allocation comes before remove complex operands. Remove complex operands, which we're going to get into today, that converts the it will pull out things that don't have atomic arguments and turn them into let bindings. So an atomic, I mean like it's a literal, like an integer. It's a variable. And I think those are the two atomic types. Now there's also, you know, of course, booleans and void, and now we'll have vectors as well, those are variables in this sense. So like we wouldn't have to worry about the I don't know what I'm trying to say. Anyway, so that ensures that when you do primitive operations, that you're not trying to do a sequence of them. You've slurped out the sequence and like made it explicit rather than being implicit in kind of a nested expression. So that's, you know, we're gonna have to get into that. But we aren't treating integer literals in any special way at this point. So I don't know how they constructed this, like what they did to get this, where this 42 did not become a let binding. Because everything else, if you notice how this vector, this inner vector, is turned into a let binding, but it's an argument of here. So like, did they inject a rubric where it's like, hey, if it's just a literal, you can, you know, you don't have to create a let binding for it. At what point do they make that distinction? I don't know. Regardless, what I want to see here is not, did we get exactly the same output as this? barring variable names. I don't care about the order, the variable names really, other than if they indicate something that's wrong with my algorithm. I want to see, does it like logically make sense? Okay, so just going outward in. So we have the vector ref, the two vector ref operations, which we expect, and those both have their second argument of 0, a literal integer of 0. So that makes sense. Excuse me. Okay. Let's collapse this. So we're binding vec init 5 inside this expression. So whatever the result of this is bound to vec init 5. Okay, so let's look at what's here at the bottom. Okay, so we have a call to the garbage collector bound, so this is the bound to the throwaway variable _8. And then we allocate, so here's our allocating our outer vector. Okay, and then so this is a throwaway variable, right? We're not using this variable anywhere, but because vector set returns a void, so there's actually no point. Again, this is about sequencing. It's interesting though that like in this case we use let and not begin. Begin end would, or rather begin with a block would accomplish the same thing. That's okay, I guess. Okay, so ultimately returning alloc6, which was bound to this. So we allocated a vector. We have this vec init 5, which came from the previous let that we'll go look at in a second. And we've assigned it to slot 0 in this vector. So that means that this is the return value of this entire expression, which gets passed to the vector ref and so forth. So I think that looks correct. This is just the garbage collection code. Nothing new there. Okay. So let's look at the upper ref. So what are we binding to vec init? I'm sorry, the upper let. So we have a nested let, and so we're binding vec init 1 to 42. So this is what we'll be filling into that slot. And you can see how that recursive, like we have the outer vector and we need to allocate or give its first first argument to the vector a let binding. So we're also doing on the inner vector let vec init 1 42. That's the first slot in that vector. Okay. So again, here we're allocating the correct size for the, or we're trying to garbage collect the correct size for the vector. And then we're binding another allocate, and here the type is vector t integer t. And then we call, so here's another throwaway binding. We call vector set on this variable alloc2 in slot 0, and we give it vec init 1, which we bound up here to 42. And then we return alloc2. So alloc2 is the result of this let expression. So that's exactly what we would expect. We do have minor differences there. I don't know. I don't know what would be useful to test here. We could say, yeah, we're okay with this, and just construct it and say, hey, this is the test. Interestingly, this should fail. Does not fail the test. That's fun. Okay, so The things that I think I care about are, do the garbage collection things get injected? Are they allocating the correct sizes? I think those are the things that I care about most. It's going to be hard to do some analysis on this to make sure that the flow is correct. Like, I think that would be way too much code for a test. The other thing we can check is that when we do the allocations, that the types are correct. So what is a way that we can do this without caring about the variables? I don't know. Maybe I hate to do this, but maybe the easy way out, because I want to get to some other things, is just to do this and say P should equal, nope, equal P2. And then we just put everything in here that we need to. And I'm just going to copy that. Yeah, I'm sorry, this is going to be not exciting. But let's get all these scoped. Well, except that's going to be L, because we share that. One thing I've learned as we've worked through these, early on in this series, we did a lot of functions that just converted one enum into, I say enum, one struct into another in a different module when they were actually had the same definition. And I wish I had done something. I wish I had done sooner is reuse those definitions more. And we started to do that with the like x86 base. So things like certain constants. I want to say constant is not the right word because it's a value. With a constructor, but we had, the first one I think I really went hard on that was the comparison operators, because those don't really change until you are emitting instructions. Gosh, and even then they don't. They may not even change then. So it was it made sense for that comparison primitive to be shared top to bottom. Okay, so we can get rid of this now, and let's run that test. We've gotten rid of the echo, so Obviously, it doesn't fail because we just copied the output. But okay, there we're done. But I think that if I had to go back and do some of that stuff again, I would use less translation functions, and I'd find out what was common between the different passes and try to pull that up. Okay, so we have that. So we'll test expose allocation. Okay, let's look at remove complex operands. So this is where things get usually spicy. So again, we need to create another intermediate language. At some point, I may do a commit where I expunge the intermediate languages that we're no longer using. They are interesting for historical artifacts, but they do kind of clutter things and they make it hard to keep the tests passing. So let's make a new file, which is lmon_alloc. Okay, and then this is going to be so this is the alloc which we've been working with. Oh, here's the dummy program. Yeah. Lmon orlalloc, but in monadic normal form. Okay, so in our previous, this can be a copy of lmon while. Let's do, except we're going to call it lalloc. Or no, it's ltup. Okay, so collect, allocate, and global value should be treated as complex operands, right? Okay, so essentially those cannot be in an atomic position, so they can't be an integer, variable, boolean, or void. So let's look at figure 6.11. Okay, so they're adding to, oops, jumped too far. So they're adding to the expression non-terminal collect, allocate, and global value. Okay, so we need to import type. Isn't that fun? Okay, so this will be, so let's put collect, and I think we said we called it bytes as an integer. I think that's what we did in alloc. Here, let's just copy those. Honestly, they are the same. Okay. So that's not complicated. Okay, that's lmon_alloc. We'll look at ctup in a minute. But let's go and update our remove complex operands pass. So we need to do, I think that they skipped over some things because we need to do uncover get before we get to remove complex operands. Let's look at the diagram at the end of the chapter. Okay. Right, so shrink, uniquify, and expose allocation. I think that what we did in our test we did not. Okay, so let's, before we go and do remove complex operands, let's make sure that we've updated shrink and uniqueify, and then let's do uncover get. And then we can go to this phase. So let's look at shrink real quick. These should not be hard. Okay, so this is ltup, and then we need to add the missing patterns. I'm renaming that as L like we did in other examples, just so we make sure that we, when we go and update this next time, it's going to be less work. So we did direct imports of all these things. Is there a code action? Yeah. Let's just... I kind of want to make this so that we do less direct imports. I know it's like not that important, but remember the purpose of shrink is only to turn these and or into ifs. So thank you, folks who work on the language server, for adding that code action. I love it. I love it. Okay, so primop needs to be qualified. And finally, program. And then we don't have any direct imports. Okay, cool. So, okay, so now we have this. We need to deal with fields. So that's, we're going to do l.prim, l.vector, and this is going to be list map fields shrink expression. Vector length shrink expression v, and this needs to be wrapped with l.prim. Okay, and this will be l.prim. We technically don't allow anything but a literal integer there, but we're gonna shrink it anyway. Oh, so helpful. Okay. And again, this is about completeness. It's very unlikely that we're going to have an and in a vector set, and or, but who knows what the programmer will throw at us. We need to make sure that we do that correctly. Okay, so let's look at, there's no, well, let's just turn this into L2 and see if that test still passes. I mean, it should. What's the type error? Shrink.shrink does not accept the piped type. Line, oh, explicate control test. Yeah, let's not worry about that. Line 238. Yeah, we're down here. Honestly, we're going to get to this today, so let's just comment it all out. Okay, so we removed a bunch of tests, which we'll uncomment eventually. But we have our shrink test did not change. That makes sense. Okay. And again, this test is actually interesting with the respect that it does the transformation and then it we checking if we're preserving semantics. So these sort of examples, you know, this one does not change anything. This one switches from and to an if, but it still interprets as the same thing. And this one, you know, returns. Yeah. And it's type checking the programs after transformation, all that. Okay. All right, so we've updated shrink. Let's go to uniqueify. And we're just going to change this to L2. And then we'll see what needs to be added here. Looks like a lot of primitive operators need to be updated. And missing patterns is going to be down at the bottom. So I want to move all these primitives up to be with the rest of them. So has type, it has no, this is just a decorator, right? Why did we do this? This is so we could propagate type information through the AST, like capture it. So our type check in the high-level language, if we jump to, so we type check the program. If we type check an expression and we get a vector as the primitive operator, then we wrap it in this has type. That lets us keep track of what the types of each field are. And that also will affect the expose allocation, right? So that's what we did in a previous session. Okay, so we're going to say, yeah, let's just do let value 1 counter 1 uniqueify expression value env counter, and then the type doesn't really have to, we don't have to do anything with that, so has type values value 1 and t and counter 1. That one was easy. Let's go back and look at these. So here we're going to say each of these fields is an expression. So ultimately we want to do return a primitive that contains vector and the updated fields, and you know, counter x. I don't know what it's going to be. We'll figure that out. Actually, we'll just say counter 1, because what we're going to do is we're going to fold. We will map fold like we did down here. In fact, let's just copy this. Fields 1, fields, and we're done. Okay, let's look at vector length. This one should be simple. It's funny with all these, the way that this, like map fold and fold, they expect the accumulator first. It's been making me wonder whether we should swap the return values of those on uniquify expression, but that's a lot of work right now. It could make this code a lot cleaner, I think. At some point we may do that. Okay, so we're gonna v, env, and counter, and then we'll return prim vector length v1, and we'll return counter 1. We could also do something funky like pipe v to uniquify expression, and then pipe the result to, you know, map pair.map left or something like that. What is that? Let's see. Pair map first. Let's try that. Let's comment this out for a second and try that. So let's say v, pipe it to uniquify expression, env counter, pipe that to pair map first, and we'll say l.prim l.vector length. The thing is, like, yeah, it doesn't have this sort of thing unless we can say can we do this? That's not a valid function expression. What's the syntax error? Yeah. Okay. Well, we'll back that out. That was a fun idea, but we'll do it the straightforward way. All right, just two more to do on uniquify. You know, sometimes I feel like, oh gosh, there's got to be a more expressive way to do this sort of thing. But sometimes there isn't, right? And that's okay. Sometimes it's better just to have clarity in your code. In this case, like, yeah, this isn't the greatest. I'm not real happy with it. This vector set. But it's clear that what we're doing is we're distributing this uniqueify expression over this, and we're sequencing it such that we can generate unique variables using this counter and they'll never collide, etc. And yeah. All right, so uniqueify, let's look at our tests for this and see what we need to fix. So this will be altup. And that should be sufficient. Yep. Okay. I don't want to do this right now. Say as L and see if we can do that on this. No, you can't do it on that position, so we'll just leave it the way it is. I would love to to qualify all of these with that alias. It's okay though. Okay, so now we're caught up to here. Expose allocation should come next. Okay, so let's go, before we get to remove complex operands, let's do uncover get. We'll make a commit and then we'll work on remove complex operands because I think that's more interesting. Uncover get doesn't do very much, but we still need to do we're going to say altup, right? No, it takes alloc. Interesting. And then it's going to produce alloc. So if we don't have get bang in alloc, we need to add that. That's going to cause some interesting changes. So let's look at while get, and yeah, it's just that. I'm going to put that up next to set bang. Okay, and then we're probably going to have some yeah, so this doesn't actually change. So let's do lget and replace all of it with L. And then we don't need that. But we need to fill out all the other we need to fill out the rest of this. And missing patterns. So interestingly, this is like, we shouldn't have that in there yet, but we have to cover it, right? So let's just put it way up here. And I think I want to combine these. So what we can do is just say underscore here. We don't care about what it is. And let's combine these clauses. And this is just like, we don't need to change it, right? All these other things we need to get down into them. Okay, so This does not contain any variable references. It can also be added, that first clause. Don't need to transform anything in there. Actually, same with collect and global values. So let's we're gonna have to let the formatter do its magic here in a second. Okay, now it's on separate lines. Okay. I'm on the fence about has type because that's only a decoration, and we should have already Truth is, it actually needs to be processed. So we'll recurse into that. Let's get this down at the bottom, or maybe we'll put it up here. Doesn't actually matter that much, but having the primitive operations all together makes sense. Interestingly, this is probably going to put a get bang because we have mutated things. That'll be interesting. Oops, index. And the last one. Okay, and then we can fix collect bang, collect set bang. Well, let's just fill it out. Okay, so is there a code action to combine those? Nope. We're going to do like what we did before. Anything that doesn't introduce a new variable. We can combine those clauses. So that means we can put yeah. Interestingly, like, we shouldn't have any get bangs in at this point. Remember earlier in this session when I was talking about, well, your guardrails are taken off. Here's a case where this can never exist. Interestingly, maybe what we should do is in both of these cases, and I think I'm going to add this. there's a longer sort of discussion, maybe we've had it before, about where is it appropriate to use a panic. We in this case I want to say we should not have any get bangs in the language yet. We want to reuse the data structure, the AST data structure, to be the same, so that we don't have to have another module defining a language that just has one fewer expression type in it, or expression variant. But we have to handle it for exhaustiveness, in this case expression. So I think that it makes sense to panic on that. Okay, so now we're going to, this is going to be, so, okay, what we were about to do before I thought to change that is these three things don't generate any new variables. They're only generated by our internal pass. So what we can do is put them here. And then, you know, put underscores in all of their slots, all their fields, because they don't generate any variables that could be mutated inside them. Okay, so this one we just do set. Well, let's actually just say this is collect set bang on value. We don't care about t. And let's finish up the rest of these. So note that, like, that's probably unnecessary for this, but it's okay. Here, we're going to do this as a pipe expression. So we're going to say v collect set bang, pipe it to set union with collect set bang on index, and pipe that to set union on value. Okay. So we've updated uncover get. Let's look at the test. It's probably going to be broken. Yeah, so we're going to say, and here I actually commented out a lot of things. So let's Okay, what we're going to do is we're going to say L tup is L. We're getting rid of that. Or no. L alloc is L. Okay. But now we need to replace LG with L dot, because we're not changing the representation. Parsed, we need to make sure that when we parse this, we pass it through the other phases. This is going to change some things here. We're going to get variables uniquely named and such. But the big thing is we have to pass it through expose allocation. The interesting thing is we might be able to skip the shrink and uniquify for these tests. Yeah, let's pass it through expose allocation to make the types pass, and then the variables won't be renamed. Because this is more about like how are you discovering what variables have changed or have been mutated. Yeah, okay. So we yeah. Didn't have to change much in that test. Okay, so we fixed shrink, uniquify, and uncover get. Let me make sure that these tests have been updated. Yeah. Okay. Okay, so we're going to say update shrink, uniquify, and uncover get phases, passes. Okay. So we still need to define almon alloc, which will be in that'll be our output of our remove complex operands. So our input language here will be alloc, and our output will be almon alloc. Okay. And then, you know, so much of this is about filling in this stuff mechanically. So let's go back up to this section in the book. Let's keep going. Okay. Yeah, so collect, allocate, and global value should be treated as complex operands. And again, we just added this to almon alloc, which is collect, allocate, and global value. So here, looking at RCO expressions, okay, so yeah, let's look at this. Remember, integers, variables, booleans, and voids can only be atomic, and so these primitive operators. The interesting thing here is that what we don't have is we need to add okay, I feel like there's something missing here, and that is what are the other operators? Because we can't just drop. Note that these are in C2, but they're not in Elmon alloc. Like in the transformation between these two is to make sure that all of the primitive operators take atomic expressions. Okay, so let's think about this. I feel like we need vector ref and vector set and vector length in here. And yeah, note here in C2 they have those primitives and they have atomics. Obviously global value. So I think that there's just a mistake here in that, you know, collect. Maybe I need to just go look at an updated version of the book here. I can also look at the hard copy real quick. Let me grab that. This could just be an error in edits of the updated version of the book. So no, it has the same error. Note also this trailing parenthesis there. That's a bug in the book. Yeah, these, I don't see how you have the primitive disappear in one phase and then it's supposed to show up again in the next phase, which is like this C2 language is going to be the output of the explicate control phase, right? So that's going to be turning our sort of like functional expression oriented nested thing into you know, a imperative like language that they call like the three address code. But so we need to make sure that we have the additional primitives in here. I think it's just a typo in the book. Let's have a look at their, really quick, I don't want to go too deep down this rabbit hole, but let's have a look at their IU compiler course. Let's look at the LaTeX. And actually there's a release, that's 2023, so we might need to contribute back. Okay, well let's look at the LaTeX and see if we can find that diagram. And I don't know if this pulls in other files or if it's just massive. No, it's just massive. Okay, and that may not even be enough lines to cover the whole book, but okay, I think that there's actually more Is this in a figure? Nope. I think this is probably a rabbit hole we don't need to go down into. Let's just look for expose allocation. Okay. So here we are, getting there. Looking at Python edition. Yeah, I they have a lot of defs. Let's see if we can find that. Yeah, that's not helping. Okay, well let's see two. Okay, I'm getting lost here. Let's just ignore that for now. I think that it's pretty clear we need to have these three operators in the monadic form. It's just that vector length needs to be given this, vector length needs to have an atomic, vector set has to have an atomic, and then we should also probably check here that vector set and vector ref have integer arguments. I think that I want to say that we check that at a higher level. Let's see. Right, we checked it as a vector type. Okay, so check vector index. Right, so we're looking at the expression. We've already checked that it has to be a literal integer expression, so I'm not concerned about that. As long as we're calling our type checker, we should be fine. Okay, so here, let's close others. We want to look at this. So we need to add to the primitive operators. It feels weird to do this because these, with the exception of read, they feel very much like this directly corresponds to some kind of like assembly instruction, right? But but we're not going to do that. Okay, so we need, and I'm going to copy these, and then we'll make sure that they follow this. So here it needs to be an atom, index needs to be an atom, vector set needs to be an atom. We've already verified in that higher level that, I'm sorry, I need vector length, that these are always integers, because we did that in that type check. Okay, so now we need to do the transformation. Okay, so let's start here by going into here and add missing patterns. Okay, so allocate. Just becomes that. Easy enough. Yeah. Yep. Okay. Collect simple translation. What's wrong with those? Oh, right. So we need to return, the return value here is different. So we don't create any new bindings. Right, so these things, we'll actually put them up at the top. Okay, same with global value. Name, no new bindings, counter. And has type we need to recurse into here. So this is really just so collect, these should be treated as complex operands. Oh, okay. So it says, okay, so if they have to be, if they're complex operands, then that means okay. Now, interestingly, I don't think that we're creating any sorry, it keeps jumping when I click over there because there's a figure right there. Okay, so honestly, I'm actually doing this wrong. Let's go up here. Okay, so this is RCO atom. I was thinking of this wrong. RCO expression, we don't have to, in expression position. In atom position, we need to deal with these. So let me just remove them and we'll re-add the patterns. So if this is in atomic position, what we say is new var, new counter, sort of what we did with the some of the other things, and we'll say this is var, new var, And then what our new var is bound to is this allocate amount and t, and then we have a new counter. And we'll do the same thing for collect and for global value, because this, for some reason I thought LCO expression came, or RCO expression came first, but it does not. Remember the point of this phase is to make sure that when anything is inside a primitive operation, that you bind it to a variable first, so that all the inputs to primitive operations can be atomic. And by atomic, we mean that it's a literal, or it's a register, or it's a place on the stack, or it's like some kind of memory location, right? It is indivisible. It is not, well, compute all these other things and then use that as an argument. It's already atomic. Okay. All right. And let's do the same here. New counter. Now, for has type, we know that this is only wrapped around vectors. So we really only care about the inner value, right? We don't care about keeping the type around. In fact, we don't have that in here. As far as I know, it's not, there is no, the type information is thrown away. It's erased. So, so we just ignore the type at this point, and we throw it away. Okay, now we need to do the same on the expression level. So expression needs to return an expression and a counter. Okay, well, we know that we can just add the missing patterns here. Okay, so these should be straightforward. These just are unchanged. Counter. And we do something similar here. This is what I was trying to do a moment ago in the wrong function. Because these are not required to be atomic in this spot. So we can just return them unchanged. Okay, so for has type, again, we're going to throw it away. So we're going to call RCO expression on value and counter. And so we just delegate. Oh, sorry, almon. Ow. Okay. And we don't care about the type anymore. Again, we're throwing away type information at this phase. So vector length, vector v needs to be atomic. So we need to do like what we did with, say, like this. So let's do something like this. So we're going to take the v, that needs to be atomic. L prim L vector length atomic. Okay, and we'll do something similar for, yeah, so like this will kind of be like that, right? Vector ref will be easier. So let's say vatom. Let's take v, and let index atom yeah, let's just shadow it. I don't actually care that much. So we're gonna say we're gonna pull this out. We're gonna say bindings list append bindings 1 and pipe that to list fold. And our inner here is going to take vector ref almon, sorry. And vatom index atom. Okay, again, this is like, make sure that each of these arguments are atomic, and then roll up their bindings if they created any, and wrap this expression with lets for those new bindings. That's what this phase does. Okay, and then we're going to do what do we do up here? Okay, atom A, atom B, okay. Why did you not work? Okay. All right, let's copy this because we're just going to do it again with more stuff. This is going to be vector set. Okay. Oh, right. This is list fold. We need to do fold right so that we preserve the order of this, of the bindings. Like, because if we want left to right evaluation within this expression, we need to make sure that the outer ones are bound first, and then we evaluate the inner ones. So that needs to be fold right. And honestly, even here, like, it's fine because there's probably only one binding. But we should be using fold right in all of these places. Okay, so let's look at the test, and it's gonna be broken. Okay, so we're gonna rename this, or not rename, we're gonna change this to almon alloc. Okay, and L while is going to be L dup. L while get is going to be L alloc. All right, then I suspect we have some, yeah, we have some tests that we commented out. So let's uncomment those. And then what's the error here? Type mismatch. Okay, so let's go here. Right, so we need to add expose allocation into that, and then that should solve that problem. Okay, so those tests still pass. The question now is, what do we expect for, because we did this for loops, right? We did a loop test. Yeah, so there's loops here. That's not about loops, but that's about set. It's about mutation. Let's make a new test here, because I think that this is important. What we want to test is that okay. We want to test that we get atomics. So we could do some simple programs with creating a vector, vector ref, vector set, and so forth. We could even take our original, like the sample program they're using up here. Like this one. Okay, so let's do we're going to get parsed. Okay. So now if we pass P to remove complex operands, the problem is this is getting really complicated. And remember in our last test that we did, like this, yikes, right? Yikes. What we might want to do is construct some simple things like this, and pass them to remove complex operands and see what we get. I mean, we could do that one, but I don't know. The other thing we need to do here is that should be okay, and then we're going to have to say l.type check. Here, type check program. Because we want to make sure that we have the has type thing on there as we go to shrink and uniquify and expose allocation and uncover get. Okay. What can we do that's a simple enough program? I think that we could shrink this one down. We could do something like what I was thinking was we would just get like an expression like this and update it. Yeah, let's do that, because what we want to see. Okay. I want to see these this program will not check. Let's just say we're just going to be testing this global value and maybe the collect. But let's say int 42. Let's remove collect from here. 43. So I don't actually care about the what I want to see is this gets pulled out and this gets pulled out, right? Into let bindings. So okay, so we're gonna have a program, and what does our new var do? It just says temp dot. Okay, so we can say that this will get extracted. Since we're doing it left to right, it'll be temp dot one. So let's do l dot let temp dot one, and that's going to be l dot global value free pointer, right? Or free PTR. And then we're going to have another one which pulls this one out. So this is a temp.2 from space end. And I'm just going to say global value is complex. Okay, and then we'll have the if, the original if, which is going to have a comp lt l.prim l.plus var. Oh wait, this needs to be lmon. I'm sorry. It's one of those weekends where I'm just out of sorts. Why is it so red underliney? It's because you're using the wrong type, bozo. Okay. Okay. And I was like, the clue was, oh, this is not producing an atomic. So here, this is going to be temp.1, right? And then we'll have an integer, which is 16. Okay, the other part of the if is so we also have another transformation, which is this is an expression. So like, yeah, it's expecting an atom here. So we're going to be pulling this out, right? This whole expression out. So we're going to have another let here. Temp.3. And here's where I need to think about how the algorithm will work. Because I think it'll pull up these variables first. Let's just go with it, and I don't know about the order of naming here, but temp.3 is going to be, that's going to be this, right? So that's going to be variable temp.1. Okay, so that's going to be an expression. So then we will do okay, now we're getting somewhere. It's like, oh, you got 3 arguments. Okay, so now we can do the if, right? And this expression doesn't have to be atomic, but and it helps if I'm using the right one. Again, goodness, we're gonna have to end the stream after this because I'm losing it. Okay, so comp takes 2 atoms. So here we need to do, we bound temp.3, right? And then we pulled out temp.2. And then the if, and then we have lint 42 and lint 43. And the only thing that except this is going to be wrapping. We need to lift those up into atomics, or into expressions, so they need the atomic wrapper around them. Oh, man. Okay, last one where I misused the module. Okay, so the only thing that I expect to be different here is potentially the order within which these are bound. And I feel okay if there's a little bit of difference there, because we thought through what the transformation does, which is this is a complex expression, this is a complex expression, this is a complex expression, and those should all be pulled out into let bindings, so that we get closer to something that's more like sequential, right? You can see here that it's like, you know, grab this global value and store it into like a register or a place on the stack, and grab this global value and store it into a place on the register on the stack, and then do this addition and stored that into a place into a register on the stack, and then take the step, the previous step, and the step before that, and compare those two, and then return one of these two values. So let's see if we're right. Okay, so we got a difference here. Let's look at what the difference is. And I think it's just an order of let bindings problem. Okay. Interesting. So it did not flatten as we expected. And I think that has to come down to, like, we're not doing explicate control here. We are just making sure that all the arguments to primitive operators are atomic. So that makes sense to me. Oh, and because it went into this expression first, right? It first does this binding and then this binding, and that makes sense. But we produce we don't produce this flattened let. Like, this is what you would kind of think would happen. But the if, like, we don't nest the if inside. The if doesn't require this to be atomic or even, like, simplified. So basically all of this stuff can go inside that first part of the if. Okay. Well, let's rewrite. And I'm going to cut all that out. So we keep the if, which I should have known. And we'll leave a hole there for a second. And we know that it's going to be atomic. Okay. So I'm going to ignore that for a second and think about what we'll do here. So we're working on this inner expression. So let's build a let for that global value. It's the very first thing. And then what we want is to replace that in this expression. Except I'm using the wrong frickin' module again. I cannot fix that on myself today. Okay, so this will be temp.1. And then this will be (16). Okay, so that's this part. And then we need to bind this part. Interesting that we have an additional let here. Oh, right, because this is not right. So we need to wrap that. So here's where attempt 2 comes in. So we're binding the result of that expression so that we can use it in the next part, which, comma there. We need to bind temp3, which is from space end. And then finally, we're going to do the comparison. So okay, so that's what we would expect. I think that, you know, I retyped it. Like, I could have just added things. I felt like I wanted to think it through. Why we get this inner nesting, it's because this expression is being pulled out. But we went into this expression and we pulled out this complex expression first, so that's why it gets temp1. And then it's not the flattened kind of sequential thing that we had before, because we're not trying to flatten it into sequential code here. We're trying to just get all of the operators simplified. Okay, and now we match. And there is sort of a question of, did I cheat here? This is not a class. We're not taking a class. We're just trying to learn. And I have encountered this sort of unexpected transformation before, because the intuition is different than what the code actually needs to do. The intuition is, oh, you like slurp all the bindings up at the top and then you flatten it down to this last expression. Well, like, eventually we'll do that. But here we don't need to. Like, explicate control will pull this part out and make it happen first. Right? That's what explicate control will do. But remove complex operands doesn't do that. It doesn't do that. Okay. This is chapter 6.4. And I feel like we took a long time to get to here. But we did a lot. And this is probably a good place to stop the stream, because I would love to go on to explicate control. It's like one of the, every single chapter we come back to it, it is the craziest transformation, the hardest to like conceptualize. But I'm not going to be able to do it in 5 minutes. And I think that would be a waste of our time. Now, it will be interesting. We'll jump onto that next time. And we'll get our thing flattened, like this nested lets, and it turns into, something like that, the 3 address code. Okay. Thank you for attending, and I will see you next week, I hope. Have a great Sunday. Bye.